What if the very fabric of reality is far more fluid and, frankly, strange than our everyday intuition can even comprehend?
Yeah, that's really the core of it.
That's the fascinating question at the heart of our deep dive today. Welcome to the deep dive. We take complex ideas, try to strip away the jargon, and find those surprising connections that, really make the knowledge stick.
Absolutely.
Today, we're plunging into quantum waves, from principles to technology. And this isn't just obscure physics for physicists.
Not at all.
It's about how this paradigm-shattering concept completely reshaped how we see the universe, and, maybe more surprisingly, how it underpins nearly every piece of modern tech you use.
It's everywhere, really.
So we've gone through the source material pretty meticulously for this deep dive, trying to pull out the most profound insights, but also the practical stuff.
Right, the so what factor.
Exactly, our mission, to kind of trace this incredible journey from the moment classical physics just clearly broke down.
Yeah, hit a wall.
To the, mind-bending reality of quantum waves, and then show how these bizarre principles didn't just stay in textbooks. They actually sparked two major technological revolutions that built our present and are now shaping our future.
It's a fascinating story, moving from pure theory to tangible tech.
So if you're ready to quickly grasp some complex ideas, maybe uncover a few surprising facts, and connect the dots without feeling totally overwhelmed, you're definitely in the right place. Let's try and make this abstract world a bit more accessible.
Sounds good. Where should we start?
Okay, so let's jump back. Picture the scientific world around the turn of the 20th century. You had Newtonian mechanics, Maxwell's electromagnetism. It all seemed pretty sewn up, right?
Oh, yeah. It was a universe of elegant certainty, very deterministic. Particles were just particles.
Yeah.
Little points moving predictably, like billiard balls.
Right. And waves were waves, continuous disturbances like ripples on a pond. Everything had its place, nice and tidy.
Exactly. But that tidy separation, well, is about to completely fall apart. The first big crack appeared with something called the ultraviolet catastrophe.
Right, the blackbody radiation problem.
Precisely. Classical physics, specifically the Rayleigh-Jeans law, made this completely absurd prediction. It said a hot object, a blackbody, should spew out an infinite amount of energy at high frequencies, like in the ultraviolet range.
Which obviously doesn't happen. You'd get instantly vaporized just standing near a fireplace if that were true.
Exactly. It was a total theoretical disaster. A huge red flag saying, hold on, something fundamental is wrong here. The classical picture just couldn't explain it.
So what was the fix? The sort of desperate measure that kicked off the whole quantum thing?
Well, in 1900, Max Planck came along.
Mm-hmm.
And apparently he wasn't even entirely comfortable with his own idea initially, but he proposed something truly radical.
Okay.
He suggested energy isn't continuous, it's quantized, meaning energy only comes in discrete packets, little chunks, which he called quanta. The energy of each packet was tied to frequency. E equals n times h times f, where h is this new fundamental constant, Planck's constant, n is just an integer, and f is the frequency.
So not a smooth ramp of energy, but like steps.
Exactly like steps. It wasn't just some mathematical trick to fix the blackbody problem. It was the first real tremor shaking the foundations of classical physics. It hinted that reality at its smallest scales wasn't smooth and continuous, but maybe more like pixelated.
Wow. That completely changes things. Energy itself comes in chunks.
Yeah.
And then Einstein picked up on this, didn't he? With the photoelectric effect.
He did, yeah. 5 years later, 1905, Einstein took Planck's quantum idea and ran with it to explain something else classical physics couldn't handle, the photoelectric effect.
That's where light hitting metal kicks out electrons, right?
Right. But the weird part was, experiments showed it only worked if the light's frequency was high enough, above a certain threshold. The intensity, how bright the light was, didn't matter below that threshold.
So a dim blue light could do it, but a super bright red light couldn't. That seems backwards classically.
Completely backwards. Classically, brighter light means more energy, so it should have worked. Einstein proposed that light itself is made of these discrete energy packets, Planck's quanta, essentially, which we now call photons. Each photon has energy, EAH.
Ah, so it's the energy per packet that matters.
Precisely. Only a photon with enough energy, high enough frequency, could knock an electron out. More intensity just meant more photons. But if each one didn't have the minimum energy, nothing happened. It brilliantly explained the frequency threshold.
Okay, so light, which everyone knew was a wave. I mean, diffraction, interference, all that.
Textbook wave behavior, yeah.
Now it's acting like a particle, a photon.
Yeah.
How did physicists even deal with that? It sounds like a flat-out contradiction.
It was a massive crisis. You had undeniable wave behavior and now equally undeniable particle behavior. The classical boxes just didn't fit anymore.
So what was the answer?
The answer, the new framework, was wave-particle duality. It basically says quantum things aren't either particles or waves. There's something else. A weird hybrid that shows one face or the other depending on how you interact with it, how you measure it.
Okay, that's already bending my brain a bit. So light is this weird wave-particle thing, but did anyone think, could it work the other way? Could things we thought were just particles, like electrons, maybe act like waves too?
That is exactly the brilliant symmetrical leap made by Louis de Broglie, a French physicist, in 1924.
Okay.
He basically said, look, nature loves symmetry. If light, this thing we call a wave, can act like a particle, then particles like electrons surely must have some kind of wave-like nature too.
That's a bold idea. Did he have, like, an equation for that?
He did. It's incredibly simple and elegant.
Huh.
He proposed that any moving particle has an associated matter wave, and its wavelength lambda is given by reshaped.
It just, again, Planck's constant.
Yep, divided by p, the particle's momentum. So it directly links a wave property, wavelength, to a particle property, momentum. It's like a mathematical bridge between those two worlds.
Okay, E's HPP. So if an electron moving has a wavelength, why don't we see everyday objects diffracting? Like, if I throw a baseball, why doesn't it spread out like a wave going through a doorway?
Yeah, that would make sports interesting. The reason is scale, basically momentum. For something like a baseball, its mass, and therefore its momentum p, is absolutely enormous compared to Planck's constant h.
So the wavelength is tiny.
Infinitesimally small. Way, way smaller than an atomic nucleus, completely undetectable. But for something like an electron, its mass is minuscule, so its momentum is much smaller. And the resulting de Broglie wavelength can actually be comparable to the size of atoms or the spacing between atoms in a crystal.
Which means you could potentially detect it.
Exactly. It becomes significant at the microscopic scale.
Now, this next bit, this feels like one of those moments where things just clicked. Before de Broglie, you had Niels Bohr's model of the atom. Electrons in specific orbits, quantized energy levels.
Right, the Bohr model. A huge step, but it had some slightly arbitrary feeling rules.
Yeah, like why did the electron's angular momentum have to be quantized? Bohr kind of put it in by hand because it matched the experimental data, right? It wasn't derived from anything deeper.
Pretty much, yeah. It worked, but the why was missing.
Did de Broglie's waves provide that why?
Absolutely. This is where it gets really beautiful. De Broglie thought about standing waves, like on a guitar string. It can only vibrate at specific frequencies, specific wavelengths that fit perfectly between the fixed ends.
Okay.
He reasoned that for an electron's orbit around a nucleus to be stable, its matter wave had to wrap around the nucleus and form a stable standing wave. Had to connect back onto itself smoothly.
Meaning the circumference of the orbit.
Had to be an exact whole number multiple of the electron's wavelength. So 2 pro r is an integer, 1, 2, 3.
Okay, wait. If you take that condition, 2 pre-ill, and you substitute de Broglie's wavelength, OHP or HMV,
Go on.
you get 2 pore in NHMV. Rearrange that. Move MV to the left, 2 to the right. You get MV equals NH2. That's right. That's Bohr's quantization rule for angular momentum.
Bingo. Exactly. Was just an ad hoc rule in Bohr's model suddenly became a natural, necessary consequence of the electron behaving like a wave and forming a standing wave around the nucleus. It wasn't arbitrary anymore. It was fundamental.
That's genuinely mind-blowing. It just emerges from the wave nature.
It was a stunning insight, and it wasn't just theory for long. In 1927, 2 American physicists, Davisson and Germer.
Yes, the experiment.
They were actually studying how electrons scattered off a nickel crystal. And purely by accident, due to an equipment issue that crystallized their nickel target, they observed something amazing. The scattered electrons weren't just bouncing off randomly. They formed a distinct diffraction pattern.
Just like waves would, like X-rays.
Exactly like X-rays, which were known waves. The pattern perfectly matched what you'd expect if the electrons had the wavelength predicted by de Broglie's formula. It was direct, undeniable proof of the wave nature of matter. Wave-particle duality was here to stay.
Okay, so particles are waves, waves are particles. It's this duality. What's the actual mathematical object that describes this? What is the quantum thing?
Right, we need a language for this. That language is built around the wave function. It's usually written as the Greek letter A, psi.
Psi. Okay, and that contains everything about the system.
Basically, yes. The wave function is supposed to be the complete description of a quantum system state. It holds all the information you can possibly know about it. But, and this is a huge, but it's not a physical wave like a water wave or a sound wave.
How is it different then? What makes it so weird?
Well, first off, it's complex valued. That means at every point in space, or configuration space, it assigns a complex number, a number with a real part and an imaginary part. We call this the probability amplitude. Physical waves have real valued amplitudes, like displacement.
Okay, complex numbers, that's already abstract.
And it gets more abstract. For a system with, say, n particles, the wave function doesn't just exist in our familiar 3 dimensions. It lives in a mathematical space called configuration space, or more formally, Hilbert space.
Hilbert space.
Yeah, think of it less like physical space and more like a vast multi-dimensional map of all possible states the system could be in. For n particles, it could have 3n dimensions. It's not somewhere you can point. It's an abstract landscape of possibilities.
Whoa. Okay, so this wave function, the psi, is like a wave of potentiality. It's not something you can directly see or measure itself.
Exactly. You hit the nail on the head. It's an abstract encoding of potentiality or information. You can't put a probe on it and measure its height. We only access the information it contains indirectly through the act of measurement, which then gives us a probabilistic outcome based on that wave function.
And it represents a superposition, like multiple possibilities at once.
Yes, because the math allows for it. A system can exist in a superposition of many different states simultaneously, all encoded within that single wave function. And for it to make sense physically, the wave function has to be normalized.
Meaning?
Meaning, if you calculate the probability of finding the particle anywhere in all of space, the total probability has to add up to 1, or 100%. The particle has to be somewhere.
Okay, so we have this abstract, multi-dimensional wave of potentiality. How does it change over time? How does it evolve? That must be where the Schrödinger equation comes in.
Precisely. The Schrödinger equation is the fundamental law of motion in quantum mechanics, analogous to Newton's ESMA in classical physics. But instead of predicting a precise trajectory,
it predicts how the wave function changes.
Exactly. It predicts the future evolution of this wave of potentiality over time. It tells you how the probabilities for all possible outcomes will change.
How does it, broadly speaking, work without getting lost in the equations?
Conceptually, you can think of it like this. You take the classical ideas of energy and momentum, but you replace them with mathematical operators. These operators are like instructions. When you apply this operator to the wave function, here's how you extract information about the energy, or momentum, or position.
So you're not dealing with numbers directly, but with these instruction sets.
Sort of, yeah. Applying these operators within the framework of the equation dictates how A evolves. There's a time-dependent version, the TDSE, which is the general case, describing how any wave function changes over time.
Okay.
And then, for situations where the underlying forces, the potential energy, don't change with time, it simplifies to the time-independent Schrödinger equation, TIES. Solving that equation gives you the specific stable wave functions, the allowed states, like those standing waves in the atom, and their corresponding fixed energy levels. These are often called stationary states.
Right, the quantized energy levels we talked about earlier.
Exactly. They pop out naturally from solving the TIES for a confined system.
So this brings up a really deep question. The Schrödinger equation describes how A evolves. Is that evolution deterministic? Or is quantum mechanics fundamentally random?
That's the million-dollar question. And it's at the heart of what we call the measurement problem. Here's the paradox. The evolution of the wave function itself, as described by the Schrödinger equation, is perfectly deterministic. If you know A at one time, you can, in principle, calculate it exactly at any future time. The potentialities evolve predictably. But the outcome of any single measurement you make on that system is fundamentally, irreducibly probabilistic. You can predict the odds extremely accurately if you do many measurements, but you can never predict the result of one specific measurement beforehand.
So deterministic evolution of the possibilities, but random outcome when you actually look.
Precisely. This weird dichotomy suggests that maybe measurement or observation isn't just a passive look. Maybe it's an active process that fundamentally changes things, collapsing that wave of possibilities into one concrete reality. It really blurs the line between the observer and the observed.
Okay, so if psi is this abstract probability amplitude, how do we get to the actual probability of finding something, the thing we can measure?
That crucial connection came from Max Born around 1926. It's called the Born rule. It's quite simple but profound. While EMEA itself is the complex probability amplitude, if you take its magnitude, or modulus, and square it, that's EMEA, That value gives you the probability density.
Probability density.
Yeah, basically the likelihood of finding the particle in a tiny region around a specific point in space at a specific time. So amplitude squared equals probability. That's the bridge from the abstract math to observable predictions.
And this leads right into wave function collapse, doesn't it? What actually happens according to the standard picture when you make that measurement?
Yes, collapse. This is probably the most debated and, frankly, weirdest part. Before you measure, the system is happily existing in its superposition. Maybe it's potentially here and there, spinning up and down.
The possibilities.
Right. But the moment you perform a measurement that asks, say, where is the particle, you always get a single definite answer. You find it here, not spread out. The act of measurement seems to force the system to instantaneously ditch all the other possibilities and choose one definite state. The wave function collapses from being spread out to being sharply peaked at the measured value.
And this collapse is random.
Stochastic, yes, meaning governed by the probabilities given by but the specific outcome is random. And it's discontinuous. It happens instantly, not smoothly. Crucially, this collapse process itself is not described by the deterministic Schrödinger equation.
So the equation describes the evolution between measurements, but not the measurement itself.
Exactly. That's the measurement problem in a nutshell. What counts as a measurement? Why does it cause this collapse? Is it consciousness? Is it interaction with a large system? There are many interpretations, but no universally agreed upon answer. It's a huge conceptual puzzle.
And this directly implies the observer effect, right? That just looking changes things.
Absolutely. In classical physics, we assume we can observe something without really disturbing it much. Measure a planet's position, doesn't really care. But in quantum mechanics, measurement is inherently intrusive.
How so?
To get information like which slit the electron went through, you have to interact with it. That interaction inevitably disturbs the delicate quantum state. It destroys the superposition. It forces that collapse. You learn something specific, but you fundamentally alter the system in the process. The observer isn't separate. They're part of the system interaction.
Okay. Let's connect this back to energy quantization. We said confining a particle's wave leads to discrete energies. How does the wave function picture explain that more formally?
Think about that wave function again. If a particle is free, flying through empty space, its wave function could be a nice, smooth traveling wave with pretty much any wavelength and thus any momentum and energy.
No restrictions.
Right. But now, confine it. Put it in a box or trap an electron near a nucleus with electrical forces. The wave function now has to obey boundary conditions. It has to, for instance, go to zero at the walls of the box, or decay properly far from the nucleus.
Like the guitar string fixed at both ends?
Exactly the same principle. Only certain wavelengths, certain wave shapes can fit properly within those boundaries and satisfy the conditions. These specific allowed wave shapes are the standing waves, the stationary states we mentioned.
And each allowed wave shape corresponds to a specific energy?
Yes, because wavelength is tied to momentum, by de Broglie, and momentum is tied to kinetic energy, only a discrete set of energy values are allowed, the ones corresponding to the wave functions that fit the confinement.
So the particle-in-a-box model is the classic, simple example.
It's a textbook illustration, yeah. You solve the Schrödinger equation for a particle trapped between infinitely high walls. What you find is the energy levels are quantized in 46 and 8 Mills' law, where n 1, 2, 3.
And that formula shows?
It shows three key things immediately. One, energy is discrete, determined by the integer n, the quantum number. Two, the lowest energy state, n1, isn't zero. It's 8th points, 8 millirelays. This is the 0-point energy. A confined quantum particle can never be perfectly still.
It's always jiggling a bit.
It always has some minimum kinetic energy due to its wave nature being squeezed. And three, the energy levels get further apart as the box gets smaller, L decreases. Squeeze it more, the energy goes up faster.
And applying this machinery, the Schrödinger equation, to the hydrogen atom, that must have been a huge triumph.
Oh, absolutely. A crowning achievement. When Schrödinger applied his equation to the electron wave function confined by the proton's electric field, out popped the correct energy levels, perfectly matching the frequencies of light observed in hydrogen's spectrum.
It's in the quantum numbers.
And it naturally produced the quantum numbers, NLM, that chemists and spectroscopists had been using empirically. It showed exactly why those numbers arise and what the corresponding electron wave functions, the atomic orbitals, look like in 3D. It proved quantization wasn't some weird add-on. It was an emergent property of wave mechanics and confinement.
Okay, this really gets to the core of the weirdness now. Superposition and interference. You said the Schrödinger equation is linear, which allows superposition.
That's right. Linearity is key. It means if L1 is a solution and L2 is a solution, then any combination like L1 plus B is also a valid solution, a valid state for the system to be in.
So a system can literally be in multiple states at once, like a qubit being both 0 and 1.
Exactly. A qubit state is often written LA plus AR1, meaning it has an amplitude L to be measured as 0 and an amplitude B to be measured as 1, existing as both simultaneously until measured. L plus has to equal 1, of course.
And how does this lead to interference? That seems like a wave thing.
It is a wave thing, but applied to these probability amplitudes. If a particle can take multiple paths to get from A to B, its final wave function at B is the superposition, the sum, of the wave functions associated with each path.
So you add the S for each path.
You add the complex amplitudes at total at path 1 plus at path 2 plus at tilde. And just like with light waves, these complex numbers can add up constructively if they're in phase, making the total amplitude bigger, or destructively if out of phase, making it smaller, even 0.
So you get regions where the particle is likely to be found and regions where it's forbidden.
Precisely. You get patterns of high and low probability based on the interference of these probability amplitudes, these waves of potentiality.
And the double slit experiment is the ultimate demonstration of this, right? Even sending particles through one at a time. It still blows my mind.
It's the absolute quintessential quantum experiment. You fire electrons, or even large molecules now, one by one towards a barrier with 2 slits. You expect maybe 2 bands on the screen behind it corresponding to the slits.
But you don't get that.
No. You get an interference pattern, multiple bands of high and low intensity, exactly as if a wave went through both slits simultaneously and interfered with itself. This happens even when you send the electrons through so slowly that only one is in the apparatus at any given time.
Meaning each individual electron somehow explores both paths, goes through both slits.
That's the implication. The wave function associated with that single electron evolves, goes through both slits, interferes with itself, and then collapses to a single point on the screen when it hits it, contributing to the overall pattern.
But if you try to watch which slit it goes through?
The observer effect kicks in. If you put a detector at the slits to see which path the electron takes, the very act of measurement collapses the wave function at the slits.
And the interference
vanishes. As soon as you know which slit it went through, it behaves like a simple particle again, and you just get 2 bands behind the slits, no interference. It's as if the particle knows it's being watched and decides to behave classically.
So this isn't just adding probabilities like we normally do. It's fundamentally different.
Totally different. Classically, if something can happen 2 ways, you just add the probabilities. Q total equal P1 plus P2. Quantum mechanically, you add the amplitudes first. A total equals A1 plus A2. Then you square the result to get the probability. Q total equals A1 plus 2 A2.
And that squaring introduces
an interference term. A1 plus A1 by equals A1 plus AG plus 2-1 plus D re A1 2. That last term, the interference term, depends on the phase relationship between the 2 paths. It can be positive, constructive, or negative, destructive. It has no classical analog. The mere possibility of another path existing affects the outcome, even if the particle didn't take it in a classical sense.
Okay. Brain officially bent. As if that wasn't enough, there's quantum tunneling. Particles going through barriers they shouldn't be able to cross. Classically impossible, right?
Absolutely impossible. If you roll a ball towards a hill and it doesn't have enough energy to reach the top, it just rolls back down, period. It cannot magically appear on the other side.
Quantum particles can.
Again, it comes down to the wave function. The Schrödinger equation describes F as everywhere, including inside the potential energy barrier, where classically the particle's kinetic energy would be negative in impossibility.
So the wave function doesn't just stop dead at the barrier.
No. Inside the barrier, instead of oscillating like a normal wave, the wave function becomes what we call evanescent. Its amplitude decays exponentially. It gets smaller and smaller the deeper it goes into the barrier.
But it doesn't necessarily hit 0.
Not if the barrier isn't infinitely thick or infinitely high. If the barrier is finite, the exponentially decaying wave function might still have a tiny but non-zero amplitude when it reaches the other side.
And a non-zero amplitude means?
A non-zero probability of finding the particle on the far side of the barrier. It has effectively tunneled right through an energetically forbidden region.
That's wild. Does this happen often? Is it just a weird theoretical quirk?
Oh no, it's crucial. It happens all the time in the quantum world, and is essential for many real-world phenomena. Nuclear fusion in the sun relies on protons tunneling through their mutual electrical repulsion to get close enough to fuse. Radioactive alpha decay happens because the alpha particle tunnels out of the nucleus.
Then technology, too.
Absolutely. Flash memory in your phone or USB drive works because electrons tunnel through a thin insulating layer to get trapped on a floating gate, storing a bit of information. The scanning tunneling microscope, STM, uses electrons tunneling across a tiny vacuum gap between a sharp tip and a surface to map that surface with atomic resolution.
What makes tunneling possible fundamentally? Is it just a loophole in the math?
It's really a direct consequence of the wave function needing to be well-behaved mathematically.
Yeah.
The wave function and its slope, its first derivative, have to be continuous everywhere. You can't have sudden jumps or sharp corners. Why? A sharp corner would imply an infinite second derivative, which relates to infinite kinetic energy, physically impossible. So the wave function must penetrate smoothly into the barrier, decay smoothly inside it, and emerge smoothly on the other side, even if its amplitude becomes very small. Tunneling is an unavoidable result of quantum wave mechanics.
Okay, so we've navigated through some seriously counterintuitive quantum principles: duality, superposition, collapse, tunneling. But these aren't just abstract ideas for physicists to ponder.
Not at all. Their impact on the real world, on technology, has been absolutely enormous. You can almost think of it as coming in two waves, two quantum revolutions.
Two revolutions. Okay, what was the first one?
The first quantum revolution was about understanding and harnessing the collective quantum properties of materials, usually involving huge numbers of atoms or electrons working together. This gave rise to much of the technology we consider modern.
Like lasers. They seem pretty quantum.
Definitely. Laser stands for light amplification by stimulated emission of radiation. The whole process relies on atoms having discrete, quantized energy levels. You pump atoms into an excited state, then one photon of the right energy triggers an atom to drop down, emitting an identical photon. That photon stimulates another, and you get this cascade, this amplification, producing that intense, coherent laser beam.
And semiconductors, the basis of all electronics.
Absolutely fundamental. Our entire digital world, computers, smartphones, the internet, exist because quantum mechanics allowed us to understand how electron wave functions behave inside crystal lattices. This led to the concept of energy bands and forbidden gaps.
And that lets us control conductivity.
Precisely. By doping semiconductors, adding tiny amounts of impurities, we can precisely engineer their conductivity, creating transistors, diodes, integrated circuits, the whole foundation of electronics. It's all built on manipulating electron waves in solids.
What about things like MRI in hospitals? That feels pretty advanced.
Also, first revolution, quantum. Magnetic resonance imaging relies on another quantum property, nuclear spin. Atomic nuclei act like tiny spinning magnets, and their spin orientation is quantized. It can only point in specific directions relative to an external magnetic field.
Okay.
MRI uses strong magnets to align these nuclear skins, then hits them with radio waves tuned to the exact energy difference between spin states, causing them to flip. When they flip back, they emit radio signals that depend on the surrounding chemical environment. Detecting those signals allows us to build up incredibly detailed images of soft tissues inside the body.
Amazing. And you mentioned electron microscopes and atomic clocks before.
Yep. Also, first revolution, electron microscopes use the de Broglie wavelength of electrons. Accelerate electrons fast, their wavelength becomes much shorter than visible light, allowing much higher resolution imaging down to individual atoms.
Right, Lynch P. Smaller wavelength, finer detail.
Exactly. And atomic clocks rely on the incredibly stable and precise frequencies associated with transitions between quantized energy levels in atoms, like cesium. They lock onto these frequencies to create time standards far more accurate than anything else, which is essential for things like GPS that need precise timing for triangulation.
And the tunneling devices, flash memory, and the STM.
Both harness tunneling. Flash memory traps or releases electrons via tunneling through an insulator to store zeros and ones. The STM uses the extreme sensitivity of the tunneling current across a vacuum gap to map surface topography atom by atom. That current changes exponentially with tiny changes in distance.
Okay, so that's the first revolution using Bork quantum effects. What's the second quantum revolution then?
The second quantum revolution is much more recent and in some ways more ambitious. It's about learning to control and manipulate the quantum states, the wave functions, of individual quantum systems, single atoms, single photons, single electrons.
Not just large collections, but one by one.
Right. And exploiting the really weird quantum features like superposition and entanglement directly for new purposes, this opens up entirely new possibilities for computation, communication, and sensing.
And quantum computing is the poster child for this, right? Using qubits.
It is. The core idea is the qubit, the quantum bit. Unlike a classical bit, which is either 0 or 1, A qubit can be in a superposition. Modulate plus Brenner 1. It's partly 0 and partly 1 at the same time.
So n qubits can represent
Point 2n classical states simultaneously. An n-qubit register exists in a superposition that encompasses all 2n possible combinations of zeros and ones. This gives quantum computers access to an exponentially large computational space to work in, exploring possibilities in parallel.
But how does it actually compute? If it's just a superposition, wouldn't measuring it give a random answer?
That's where the magic, or rather the physics, comes in. Quantum algorithms aren't just about storing superpositions. They're about carefully manipulating them using quantum interference.
Interference is computation.
Exactly. You design sequences of quantum operations, like laser pulses acting on trapped ions or microwave pulses on superconducting circuits, that manipulate the complex probability amplitudes associated with all those 2n states. The goal is to orchestrate a massive multi-path interference.
Okay.
You want the amplitudes corresponding to the wrong answers to interfere destructively to cancel each other out. And you want the amplitudes for the right answer to interfere constructively so its probability gets amplified, ideally close to 1. Then, when you measure at the end, the wave function collapses with very high probability onto the correct solution. It's like wave engineering in Hilbert space.
That is just profoundly different from classical computing. What are the killer apps, the big problems they might solve?
Well, the most famous is Shor's algorithm. It uses quantum interference in a clever way to factor large numbers exponentially faster than any known classical algorithm.
Yeah.
This is the one that threatens to break much of today's internet encryption.
Right, because encryption relies on factoring being hard.
Exactly. Another is Grover's algorithm, which offers a quadratic speedup for searching unstructured databases, finding a needle in a haystack faster. There are also promising applications in simulating quantum systems themselves, like designing new molecules and materials, optimization problems, and machine learning.
And quantum cryptography, that uses the observer effect for security.
Precisely. Protocols like BB84 use quantum states, often single photons in superposition states, to securely distribute a secret encryption key. The key feature is that if an eavesdropper tries to intercept and measure these photons to learn the key,
they inevitably disturb them, collapse the wave function?
Yes. The act of measuring unavoidably alters the quantum state in a way that the legitimate sender and receiver can detect by comparing notes on a subset of their measurements. If there's a high error rate, they know someone was listening, and they discard the key and start over. It offers security guaranteed by the laws of quantum physics, not just mathematical assumptions.
Yeah. Okay. We have really covered some ground today. We started with classical physics hitting a wall.
Yeah, the ultraviolet catastrophe, the photoelectric effect.
Then de Broglie's bold idea, linking particles and waves, leading to the abstract probabilistic wave function.
And the Schrödinger equation governing its evolution, but also the mystery of measurement and collapse.
And we saw how this wave nature naturally explains things that seemed bizarre, classically energy quantization from confinement, the mind-bending interference in the double-slit experiment, even particles tunneling through impossible barriers.
It's a whole new rule book for reality at the small scale.
And then we saw how these rules led to two revolutions. The first gave us lasers, transistors, MRI, basically the modern electronic age.
Built on understanding collective quantum effects.
And now this second revolution, controlling individual quantum systems, promises quantum computers, secure communication, ultra-sensitive sensors, potentially another transformative wave.
It really feels like we're just scratching the surface of what controlling quantum waves can do.
It's undeniable that quantum waves represent this profound paradigm shift. We really have to let go of our everyday classical intuition and embrace a reality that seems fundamentally described by abstract math, probability amplitudes, and, well, weirdness.
It forces you to rethink what reality even means at that level.
So maybe a final thought for you to ponder. If this quantum wave, the psi, is truly a wave of potentiality, maybe even information, and its evolution is perfectly deterministic according to Schrödinger until someone or something observes it, causing a probabilistic collapse. What does that really tell us about the fundamental nature of reality itself, and what does it say about our own role as observers within that unfolding quantum universe?
Yeah, that's the deep question, isn't it? What is the relationship between the mathematical description, the potentiality, and the concrete world we experience? It's something physicists and philosophers are still grappling with.